This video introduces NP completeness and reductions with a few different graph problems as examples. Before watching it, you should know about asymptotic notation and graphs, be familiar with algorithms in general, and you should watch the first video in the NP playlist that defines NP, at least until it starts discussing optimization algorithms versus decision algorithms, so you should know what the Clique problem is. I'll start here by defining the independent set problem. Within an undirected graph, an independent set is a set of vertices with no edges between them. If edges model dependencies of vertices, everything in the independent set will be pairwise independent. The independent set problem asks if there is an independent set of a given size in a graph. The independent set problem is in NP. If we give the independent set of size k as a certificate, we can write a polynomial time algorithm to verify that the graph doesn't have any edges between any pair of vertices in that set. It's in NP, but we don't know how to solve it in polynomial time without a certificate, so we don't know if it's in P. But suppose that we could solve the Clique problem in polynomial time. Could we use that to solve the independent set problem quickly? Well, if we have a graph with a size k independent set, and then we take the complement of that graph, which has all of the missing edges but doesn't have any of the edges from the original graph, that complement graph will have every edge between vertices in the original graph's independent set. The complement of an independent set is a clique. There are a few different types of reductions, but this is the type we're going to care about here. Given an instance of independent set, in polynomial time, we can create an instance of Clique such that the original problem and the new problem both have the same yes or no answer. We symbolize that where the less than or equal sign implies that the independent set isn't harder than the Clique problem because the Clique problem can be used to solve it. The P denotes that we're allowed to take polynomial time to transform an instance of one problem into an instance of the other. One thing that this reduction has that's a bit unusual is that it works both ways. The same transformation that changes the independent set instance into a Clique instance also reduces a Clique instance into an independent set instance because the complement of a Clique is an independent set. We're going to use a few different problems. Vertex covers up next. In a graph, a vertex covers the edges that it's a part of. A vertex cover is a set of vertices that cover all of the edges in a graph. The vertex cover problem asks if a graph has a vertex cover of a given size. Notice here, it's harder to find a small vertex cover, while it's harder to find large cliques and independent sets. But still, vertex cover is in NP. If somebody gives you a cover as a certificate, in polynomial time, we can mark edges for each vertex in that cover and then verify if all edges from the graph are marked. We can reduce independent set to vertex cover. Notice in a graph, no edges go between two vertices of an independent set. That means every edge either goes from the independent set to something not in the set, or between two things not in the set. Either way, every edge has at least one vertex not in the independent set. The vertices not in the independent set form a vertex cover. So here, there's a size 4 independent set in the graph with 7 vertices, if and only if there's a vertex cover of size 3. This reduction also happens to work both ways. Now, we know that Clique reduces to independent set, and independent set reduces to vertex cover. These reductions are transitive. Taking the composite of two polynomial time reductions gives us another polynomial time reduction. In this case, to reduce Clique to independent set, we took the complement of the graph. And then to go from independent set to vertex cover, we changed the size we were looking for. Doing both of those things gives the reduction from Clique to vertex cover. Okay, we're finally ready to define some new complexity classes. Because independent set reduces to Clique, in some sense we say that Clique is at least as hard as independent set. Now suppose that you have some problem X that is at least as hard as any NP problem. That is, for any problem in NP, we can reduce it to problem X. So X is as hard as any of them. We say that X is NP hard. Unlike NP, the NP hard complexity class is a statement of difficulty, not ease. Clique is NP hard. I won't prove that here. So now we have a statement of ease for Clique and also a statement of difficulty. If a problem is in both of these complexity classes, we say it is NP complete. So Clique is NP complete. Even though I'm not going to prove that Clique is NP hard, if we accept that it is, it becomes much easier to prove other problems are NP hard too. We already know that independent set is in NP and that Clique reduces to independent set. And we're taking it as a given that Clique is NP hard. Intuitively, if independent set is at least as hard as Clique and Clique is NP hard, so is independent set. More formally, we know that for any problem in NP, it reduces to Clique. And we know that Clique reduces to independent set, so we can take the composite of those reductions to reduce any problem in NP to independent set in polynomial time. That proves independent set is NP hard, and so it's NP complete. Similarly, we've seen reductions from Clique and independent set to vertex cover, so that's also NP hard and NP complete. That covers the basics of the definitions, but it's a bit misleading to only show you reductions that work in both directions. Those are pretty rare, so I want to show one more. In a graph, a vertex dominates itself and all adjacent vertices. In this graph, 6 dominates everything except 3. A dominating set is a set of vertices that dominate all vertices in a graph. And we can ask if a graph has a dominating set of a given size. That question is in NP. If somebody suggests a dominating set to you, mark each vertex and everything adjacent to it, and then check that all vertices of the graph are marked. So here, if I add vertex 3 to vertex 6, I can verify that those two vertices are a dominating set. It would only take linear time in the input size to check for adjacency list or adjacency matrix format. So, dominating set is in NP. Now, we want to find a reduction from vertex cover to dominating set. And it will be a bit more complex than our previous reductions. So I'm given some instance of vertex cover, maybe this graph, and I'm asked if it has a vertex cover of size 3. I need to transform this into a dominating set instance, and I'll create a pretty different looking graph for that. First, I'll move it around a bit for visibility. Considering the edge from vertex 1 to 4, for that edge I'm going to create a brand new vertex. I won't label it and I'll make it small, and I'll give it 2 edges to the 2 vertices of that original graph. Those will be part of our dominating set instance graph. It will have all of the original vertices and edges, plus one of these little vertices and 2 edges for every edge in the vertex cover instance. Let's think about these new vertices in the new dominating set graph. First, each one only dominates itself and the 2 vertices that created it. So that first vertex we added dominates only itself, 1 and 4. Meanwhile, both 1 and 4 have to dominate those same 3 vertices because by construction, each is adjacent to the other 2. But 1 and 4 might also be adjacent to other stuff. So each might dominate more. Each dominates a superset of the stuff dominated by the new vertex. Because of that, we can be sure that there's a minimum sized dominating set that only contains original vertices, because we can always replace a new vertex with one of the originals. But notice, if we have a vertex that dominates a new vertex, it covers the original edge that spawned that new vertex. A set of original vertices that dominate all of the new vertices, like 3, 4, and 6, will also dominate all the other original vertices, but they also must cover all of the edges taken directly from the original graph. They cover at least half of the new edges too, but we don't really care about those. We're looking for a vertex cover in the original graph. There's a minimum sized dominating set in the new graph that doesn't include any of the new vertices, and those vertices form a vertex cover in the original graph. If there was a smaller vertex cover in the original graph, those vertices would make a smaller dominating set in the new graph. So the size of the smallest dominating set in the new graph will be the size of the smallest vertex cover in the original. One technicality. I assume there aren't any singleton vertices with no edges in the original graph. Those vertices can be ignored in the vertex cover graph. They don't cover anything, so we shouldn't include them in our dominating set graph. A singleton in the dominating set instance must be in the solution. Nothing else dominates it. Anyway, that gives a reduction from vertex cover to dominating set. So dominating set is NP hard and NP complete. But this reduction doesn't reverse itself. Unlike the previous reductions we saw, if we apply this transformation to the dominating set graph, it doesn't transform it to a helpful vertex cover instance. And given an arbitrary graph, we can't undo the transformation that went from vertex cover to dominating set. A graph like this one doesn't have those little triangle vertices and edges to remove to get a corresponding vertex cover problem. But there has to be a reduction in the other direction, because dominating set is in NP and vertex cover is NP hard, so by the definition of NP hard, there must be some reduction from dominating set to vertex cover. This is a huge topic. The next thing to cover is a proof from scratch that some NP problem is NP hard. I took it as given that Clique is NP hard, but we should prove that. The problems we used here were all similar looking graph problems, but there are NP complete problems in pretty much any area. And you could make an entire course out of studying approximation algorithms, polynomial time algorithms that don't perfectly solve optimization versions of NP complete problems, but that can guarantee that their performance isn't too bad. Anyway, that's it for this one. My massive corns have a date with a pumice stone.